Well, happy Valentine's Day, everybody. Yes, you should all be taking your spouses out for lunch rather than coming here. But thank you all the same for coming. Okay, so I want to talk about the state of the lake, not in general, but also about this publication. This is something we do every year. We started doing it 6 years ago, in part because every year we have to produce the clarity number for Lake Tahoe, annual clarity number. And it's many of you may have seen it come out every year. It's eagerly anticipated. Everybody wants to know what it is. And it always seems strange to me that we do all this work up there, and it all comes down to one number. And we just built this center there, this LEED Platinum building, and it just seemed there was a lot of building for one number. So I thought we'd better do something to get the word out about what's being done there. So there are lots of things about Tahoe that don't change. And that's not what we report every year. So for example, we may know it's the 11th deepest lake in the world, second deepest in the U.S. Crater Lake National Park is deeper. It has a very small surrounding watershed compared to the area of the lake. There are 63 streams that come in, one leaves, doesn't flow to California, flows to California, but then it turns east and goes to Nevada. So the state of California gets no water of Lake Tahoe. Just enjoy it. Well, there are the things that don't change. What we do report on are some of the things that do change, and in particular, what these changes mean on a year-to-year basis. And there's lots of reasons, lots of good reasons to understand this change. That picture on the left, I guess Tahoe was voted the best lake by somebody. Whether it's the best lake, the second best lake in the world, or the U.S. doesn't matter. What it's really saying is it has a huge economic input, both to the region and to the state. We've all seen the Keep Tahoe Blue bumper stickers. Again, it's a cool bumper sticker to have, but it's a statement of law. What that means is under the Clean Water Act, there are things the state of California and the state of Nevada have to do to restore water quality conditions in Tahoe. And knowing what you have to restore and how to restore it is really a lot of what we do and what we try to emphasize year to year. So this is the report. It's always issued online every year. It's widely read. That's what he's reading. So this is one of my, Lawrence Bragg was one of my scientific heroes. Anyway, so one of the things he said is the important thing in science is not so much to obtain new facts, but to discover new ways of thinking about them. So we go out, we do a lot of the same measurements year in, year out. We have been doing measurements since 1958 at Tahoe. So this report isn't just adding another point or another dot. It's looking at this vast body of data and trying to think about it in terms of what's changing, whether it's climate, whether it's atmospheric deposition, whether it's population growth, and the like. Yeah, actually, Bragg was like myself. He was originally from Australia, and he went to England and lived the rest of his life there. Unlike him, he got his Nobel Prize at the age of 26. So clarity, that's one of the issues at Tahoe that everybody's always interested in. And this is what I was referring to before. This is the clarity number. So each of those circles represents an average for the year. 25, on average, 25 readings are taken under clear conditions, near the middle of the day. It's a very prescribed procedure that's used. And what you see is that going back in the late 60s, there was something like 30 meters or 100 feet of clarity. And over time, that's declined. So currently it's about 70 feet or thereabouts. And you see there's some scatter there. The number circled there, 68.9 feet, is what it was in 2011. So the 2012 report reports on what the conditions were in 2011. So it actually increased in that year to 4.5 feet, by 4.5 feet. So again, large changes often on a year-to-year basis, even in the average. But it's possible to break this down a little bit. And if you just look at the winter time, there's actually been a marked improvement. Sorry, let me just back up 1 second. Up to about 2000, this was statistically, you could put a straight line through that. And there was no reason to say it was getting better at all. The last 10 years, it's bent over. So we say it's getting worse at a much slower rate. Agencies up there would like us to say it's really getting better. But looking at this data, it doesn't appear so. You look at the winter, and it is getting better. On a statistical basis, it's improving. Winter clarity is over 80 feet. Jumps around year to year, but it is getting better. And so when we showed this to the agencies last year, they were thrilled. Finally, they were able to say, with all the millions, tens of millions, hundreds of millions of dollars that have been spent, we have a positive result. And they loved science. They loved UC Davis. And we showed them the summer results, and they didn't feel so good about us anymore. And it was like, and this is the time most people are in the lake and on the lake and around the lake. It's summer, and it's not getting better. But unlike the other two plots I showed you, a straight or a line through there, there's just so much scatter that it just doesn't look right. So clearly, there's something else going on here. I wish I could tell you what it was. And when I look at it, I see there are these decade-long periods where it rapidly gets worse, and then things change. And then it rapidly gets I think this critical update can wait. Okay. So, something is happening, whether it's climate, whether it's, I'm not sure. This is something we're actively looking at right now. There are some potential causes we can look at. So to understand the clarity, you have to understand light. Light can do a number of things in water. It could be absorbed by the water itself. So even if the lake was totally pristine, you couldn't see to the bottom. You could still only see down maybe 200 feet. It's absorbed by particles, it's scattered by particles, and some of it gets transmitted down. What everybody is trying to do is maximize the amount that gets transmitted down. Okay, a lot of work went in trying to understand the causes back in the late 90s, the sort of early part of the early 2000s. And this wasn't just UC Davis. This was a lot of funding from the state, many state agencies, many federal agencies involved. One of the things that came out of it, one of the big things, was we were able to say what's causing the decline. What pollutants are causing the decline in clarity, and more importantly, where they're coming from. Because if you're going to try to restore it, if you don't know what the source is, then you may well be spending a lot of money on the wrong things. So it turns out that very fine particles less than, it says 20 microns there, but it really should be more like 10 microns, are the main part of the problem. And where most of them come from, the 72%, are from the urban areas, the built-up areas, the places that have actually changed. 50 years ago, 100 years ago, there wasn't a road network. There weren't condominiums and shopping centers to the extent there are now. And so it actually, in a way, makes sense. So it's this urban area. It's stormwater runoff. Stormwater that previously may have been infiltrated into the ground is now running over hard surfaces, going to drains and culverts and streams and sometimes directly to the lake. Okay, so get that. Okay, so 10 microns. How big is that? Some of you don't deal in these sorts of numbers, so this is here to help you. A dog, 1 million microns. Flea, 3,000. Head of a pin, 2,000. Typical hair thickness, 100 microns. If you ever change the toner in a laser printer or a photocopier, you get that inky stuff on your hands, that's about 10 microns. So things that are just invisible on an individual basis is the size that we're talking about. Okay, now this is the most geeky part. This is where I put in a few graphs, so bear with me, because this is actually important, because if I was giving this talk 5 years ago, this part would be totally different than it is now. So before I showed you that clarity picture measured with the Secchi depth, the Secchi disk, round disk, and I showed you the average values of those circles. So this is for the last 10 years, since January 2002, and these points represent the individual measurements we take. So this is every 2 years. And so what you see, number one, is in a given year, there's lots of variation. So much variation that it's confusing to see what's happening. But typically, we get the lowest clarity in summer, better clarity winter, summer, winter, and so on. And you see towards the end there, we're starting to get lower clarity. It's going down, it's there in meters. So let's say 11 meters, about 36 feet. All right, I'm going to overlay another figure on this. Okay. This is something we do. We measure, take water samples, and we measure the clay and silt in them. Okay? And so this was there's a gap in funding there, but this is I'm sorry. Yeah. I should have a sign. Yeah. I guess the red is at 5 meters, the brown is at 20 meters. But and if you look closely, you can see when the particles go up, the clarity goes down. And so that was very exciting. It was on the basis of this data that the TMDL, this is the program to release the target for the Clean Water Act, it was on the basis of what was measured in this period. So this is actually really important data. Okay, now I've overlaid something else, green stuff. That green represents algae, little floating plants that are of the same size as these silt and clay particles. The ones that we said back here were the main contributor of the decline in clarity. And you can see back then, these particles were really low in concentration. Suddenly, in the last 4 years, these particles have exploded, gone up 1 to 2 orders of magnitude in concentration. So the lake back here, when everything was set in place for the TMDL, for the meeting the Clean Water Act, is very different than it is here. We have almost as many particles present, that are biological particles, that are fueled by nitrogen and phosphorus, than we have that are coming in from the roads. And so that's a huge thing that has changed. Now, whether it's a blip for 4 years, I don't know. But it's that blip, it's that period when clarity really has gone down, especially in the summertime when these things are prevalent. Okay, what do they look like? Well, it's a 10 micron scale, so they're right in that sweet zone of being about 4 or 5 microns. They've always been there. They're not an invasive species. They're nothing new, but they've just never been there in the same sorts of numbers and concentrations. So that's one blown up. So they're diatoms. They have a little silicon, it's called a frustule, and so they're very efficient at scattering light. Okay, so this is the winter of 2011. 2012 report describes the 2011 data. And if you remember, that was a huge winter. It was just tremendous snow. So, what impact does one winter have? Does it make things good or bad or what? So this is the long-term precipitation from Tahoe for the last 100 years. And so here we are that year, 2011. It was about the 6th wettest in the year. Now, it stands to reason, or it used to stand to reason. And we used to say this just over and over again. When you have a wet year, clarity goes down because nature is just washing all this stuff into the lake. So we're trying to build engineered systems to stop things going into the lake, but when it's a wet year, you just get a lot of it happening naturally. So here we were, a very wet year. As you saw before, clarity improved. It went up 4.5 feet. I don't know why. I really don't. You can see it went up 4.5 feet. So this decrease in these years was due to those algae, but then suddenly this last year, it got better. And just an example, this is the monthly precipitation. So the yellow was 2011, and this is 2009. So just comparing the monthly precipitation with the last few years. You just see what a monster year 2011 was. It should be washing lots of stuff into the lake. For some reason, it didn't happen that way. Okay, temperatures. So this is these are data collected, a project we have with NASA, where we have 4 buoys with them out on the lake. And we can record temperatures every 2 minutes. And so what we're presenting here is this is the data from July, the average July temperature. 2-minute data throughout. And what you see is that it peaked in about 2006. Ever since then, it's been getting cooler. That should be good news. Global warming is over. Finished. We have the proof in our time. And some people have said that when they've seen this graph, like, oh, look, it's getting cooler, because Tahoe has been used as one of the indicators of warming temperatures. But this data is showing the very opposite. And it was chosen to sort of make this somewhat controversial point. But you can ask the question, well, why is it getting cooler? Or why are the July temperatures getting so much cooler, at least in the last 4 or 5 years? And that has to do with the way the lake works, the mixing of the lake. This is another strange figure. This is the depth of the lake, this axis. And here we have data from 1973 up to the present. And what each of those bars represent is how deep the lake has mixed every winter. So right here at the beginning, there were 3 years in a row when it mixed all the way to the bottom. And then, say, this year, it only mixed to about 300 feet. So this is what happens in winter. It gets cold at the surface, it mixes. It's a really important process, in part because this is what gets oxygen to the bottom of the lake. It redistributes nutrients. It's sort of like it's like spring cleaning, if you will, for the lake. It needs this to happen every year. We'll come back to this. So we've actually had a disproportionately large number of these in the last few years. So in a way, it's this deep mixing that's can fully account for that cooling we're seeing. So it really has little to do with long-term climate. It has more to do with some of these internal workings of the lake. Okay, invasive species. So anybody heard about invasive species at Tahoe? Yeah. So what have you heard? What name a species? Quagga mussels. We don't have them, but that's actually the focus of the invasive species program, is a massive bird inspection program to keep quagga mussel out. They attach to hard surfaces and don't want to have them. What led to that was the discovery of Asian clam. The clam, it burrows into the sediment. So in a way, the Asian clam has at least heightened awareness of what needs to be of what may need to be done in the future. So this is what a lot of the sand and sediment looks like in the nearshore in Tahoe, in a pristine area. These are dead clam shells, and that green mass is like again, it's algae, but it's this long filamentous algae, and it washes up on the beach, and if you walk on the beach, you can cut your feet on the shell. So it's a nasty thing. They're about fingernail size. You can eat them, but they're tasteless. And they're just small and difficult to harvest. So they arrived probably on boats or from people dumping aquariums about 10 years ago. So this is probably the latest invasive species that's there. Attracted a lot of attention and financing from various agencies to try to, well, in the beginning they said it was to eliminate them. I think with any invasive species, it's almost impossible to eliminate them. Maybe control them is a more realistic goal. So this is Emerald Bay. They started off in the southeast corner on the border of California and Nevada. And about 2 years ago, we found them at the mouth of Emerald Bay in this area denoted in, I guess, in red there. And so the way we've devised to treat them is pretty much a scorched earth policy. But rather than burning the bottom of the lake, we lay out rubber mats, rebar on top. And what that does is that it cuts the oxygen transfer from the water into the sediment. And in a period of about 30 days, they die. They literally hold their breath for 30 days. That's in summer. In winter, they can hold their breath for even longer. It's really effective. We treated, at least designed the treatment for, I guess, 2 areas in the southeast. Just this last couple of months, we've laid down 5 acres of rubber barriers here. Turns out Emerald Bay is different. Where we were very successful, literally 99.9% mortality on the southeast. We did a little test here at Emerald Bay, and we didn't get that. We got actually 0 mortality. And the reason is that Emerald Bay, in its formation, is, I don't have a good map of it here. It's a remnant from a glacier. So basically, there was 10,000, 100,000 years ago, there was a glacier. It pushed out as far as the entrance to Emerald Bay. And so what the entrance to Emerald Bay is all the rock and debris that was left behind was being pushed ahead by this glacier. And so it's very porous. So even though we laid this rubber mat on top, there was enough water being transported through that material to keep the clams alive. So what we've done is we did another test. Here are all these rolls of black rubber. We have this biomass material. So sort of stuff you use to stop erosion on a construction project. There's these sort of mats made of aspen, native material. So now we have to roll this out first, then roll the black rubber out, and then the decomposition of the aspen is what actually ends up killing or removing the oxygen and killing the Asian clams. Okay, that's just a picture of what it looks like. Okay, we do a lot of work with computers. There's a picture of some of our young students hard at work. And this is something one of them came up with. So this is part of a 3-dimensional model for Lake Tahoe. So it's a big computer model. What it does is it solves the flows. It comes up with estimates of the flows across the lake and all the way down to the bottom, and it's driven by the meteorology. So we have 11 wind stations around the lake, and we feed this data in. So what I'm just going to show you is it's like a 2.5-day visualization from the model of what the surface does. So each of these little colored dots represents, think of it as a tennis ball. And so this quadrant of the lake has yellow tennis balls. This has light blue, dark blue, and red. When I hit go in a minute, they're going to start moving. And it's truly astounded me when I saw this, because what you're going to see is, this 2.5-day period, is the lake breathing. It's like a giant heart pumping. Ready? Do it. It's shocking how far, in 2.5 days, things move. This is what it does. And so you can see how quickly clams, little baby clams released here, could get across to Emerald Bay. It takes about 12 hours for them to move across like that. This would be happening on a day that would be perfectly calm. There aren't sort of major storms or anything like that happening. It's so good I have to show it again. A lot of people think that, well, if I do something, if there's contamination here, it's going to stay here. But very quickly, this blue stuff ends up somewhere else, which is sort of interesting now that California and Nevada are at odds over how to govern the lake. Okay. Climate change. No, this is not Lake Tahoe. But, as I said, this could have been Emerald Bay. 15,000 years ago, Emerald Bay would have looked very, very similar to this. This glacier, icebergs carving off the end of it, and so on. That's the same one that's giving you some scale of how big that is. This is actually a lagoon in Chile. All right, so climate change is happening at Tahoe. I used to like putting on the latest climate change fact. I can't keep up anymore because every day there's something about the Middle East is drying up over the last 15 years, or the ice sheet is thinning at an unprecedented rate. But I couldn't help this one, where Australia had to add a new color for temperature because it just got so hot. And so this purple area represents color, I think, 45 to 50 degrees Celsius. It's just outrageous how hot that is. So lake levels are low. This is from the Great Lakes, I guess, Lake Huron and Lake Michigan are at record lows. And so these are arguably the results of climate change, the sorts of things that could be happening to Tahoe and to every reservoir in the state, not just a 3 or 4 year drought, but possibly a decadal, multi-decadal drought. So climate change is happening at Tahoe. As I said, data from Tahoe goes back a long way. And unlike a lot of data, when you measure Tahoe, you're measuring a whole watershed. Meteorology, the streams, and the lake, all in one small area. So this is particularly the nighttime minimum temperatures have gone up pretty dramatically. Daytime temperatures, maximum, have also gone up, but not as much. And this isn't unique. This is the sort of the same kind of picture that you see from many places. I sometimes get accused of jumping on the climate change bandwagon because, there's money in it and there's fame. And one could get a lot more fame if you could present data that showed the opposite, that it's actually cooling. Getting this stuff published is difficult because it's more climate change. All right. This is actually the important thing. It's getting warmer, but so what? Ask most people, would you like to swim in a slightly warmer lake? Everybody would be in favor of that. But it affects how the lake works. It affects that breathing. It affects that mixing, that plot I showed you, the amount of mixing. How does it affect it? Well, you go back and think about the physics you took once upon a time. You know that warmer things are lighter things. So warm water is lighter than cold water. So as we get warming of the lake, the difference in temperature between the top of the lake and the bottom of the lake is increasing. So to get this mixing in winter, this ventilation, unless the wind increases a lot, we're not going to get as much mixing. So we found out we can actually, I put the wrong figure in here. Anyway, this one's good. Actually, we call this stratification when you have the top is warmer than the bottom. And typically at Tahoe, the lake would be stratified currently for about 180 days, 6 months. Sorry, that was 1965. Up to the present, that's actually increased to about, by the tune of about 10 to 12 days. So the length of time when this lake has its maximum resistance to mixing has gone up. This figure, this is the one that shouldn't be here, should be on the next one, is using these climate change models, looking out into the future. So this is using a particular model, downscaled for Tahoe. And this is using a particular assumption about carbon emissions. And so again, and I got this one mixed up. So this is actually showing the strength of this stability. So right now, its stability is something like 1,000 units. In 100 years, it's going to be 1,150 units. I'm going to skip over this because that's okay. So what of this? Again, 100 years going out into the future. This is now showing oxygen. Blue is oxygen-rich water. The red is no oxygen. So here, as we approach 2060, 2070, I don't know, because I don't know what the carbon emissions are going to be. I don't really know what the climate's going to be. But under a plausible scenario, one could see oxygen being totally removed from the bottom of Lake Tahoe for decades at a time. I always say it's a big lake. Maybe the fish and whatever needs oxygen can be happy in the upper 500 feet. What happens when you remove oxygen from the bottom is that the whole chemistry of the sediments change. And so in the absence of oxygen, you start getting releases of phosphorus. So here in the bottom figure, that's phosphorus concentration. Phosphorus is one of the things that's regulated in Lake Tahoe. Millions of dollars spent trying to control it, minimize how much gets into the lake. If we look at how much is currently coming in from urban areas, non-urban areas, from the atmosphere, groundwater, and we compare it to what could be released from climate change, it makes one think about the value sometimes of current efforts. This is what we're currently trying to control. This is what we may have to deal with in the future. Okay. So measuring all of this stuff is challenging, interesting. How are we going to do it in the future? We have lots of ideas. We have our ALO, our Autonomous Real-Time Lake Observatory. This was an idea to really instrument the lake, rather than just instrumenting a stream or having data from a buoy, there's one or two buoys here. There are ways of having things that are going up and down, rather than measuring at a point. We have these gliders. These are cool. These are like gliders. They'll go. We have one coming out for 3 months for 1 month in April. Basically, it's like a drone, and it's sort of it's like a rocket, but it has a little weight inside. So when there's a little motor, it moves the weight forward. So when the weight goes forward, it tilts forward and goes down. Okay, gets to the bottom. All the while, it's taking measurement. Gets to the bottom, it has a little bladder. Just inflates that bladder a bit, so it becomes buoyant. Moves the weight back, goes up, and so it goes down, goes up. So it can do this for months using almost no energy of things that float around and the like. All right. So conclusions. Clarity improved in 2011, but we don't know why. It's sort of embarrassing. University, we should know why. These small algal cells, somehow they're linked to the changes in the last 5 or 6 years. They're increasing, but we're not really sure why they're increasing. This is a very bad seminar for UC Davis. None of that either. Okay, so deep mixing. This deep mixing process is an important driver. It's kept the lake largely how we want it to be, but as we go forward in the future, that's going to change. We have some new modeling tools, lots of new measurement tools. Bottom line is that, I don't know who said it, but we know who the enemy is, and it's us. It's people. What's the cause of clarity decline in Lake Tahoe? It's people. What's the cause of invasive species? It's people. Everything, it's people. Doesn't mean we should put a gate there and keep people out. It just means we have to do a better job of trying to find ways of minimizing our impact. And that's what this whole TMDL process is about. I didn't talk, we have an education center. Actually, I should talk about this. We have 2 education centers at the Tahoe Basin. One is at Incline Village, and we have one in Tahoe City. So I can give you information about that. We have 3D visualizations and hands-on activities and a whole bunch of things. Okay, and this is the thing that's currently driving me nuts. Current financial situation, state, federal government, everybody's cutting back. What do they want to cut back on? Monitoring. You've got 40 years. We say we have 40, 50 years of data. Isn't that great? And they say, you've got 40 or 50 years of data. Do you have enough yet? And yeah, in a time of rapid change, this is the time when we need data more than ever. When you have a TMDL to enforce, you can't manage it if you don't know how it's changing. And so that's sort of my big thing right now. Okay, so bunch of happy people who work, but a combination of Tahoe and Davis. The actual funding of this report, we somehow scrounge money together to produce it. We got a gift from the California Tahoe Conservancy last year to partly offset those funds, those costs, and that's it. So reach me there. And happy to take questions. Yeah. Yeah. There was a PhD student at Berkeley about 15 years ago, Mark Butel, who took a sediment core from Tahoe and basically came up with a release rate. It's, as far as the actual size of the pool, it's infinite. I mean, the lake is 2 million years old. It's just whatever's gone in is there. So it's not as if the oxygen disappeared, that the phosphorus would be sort of burnt off in 5 years or 10 years. So it's, it is. Yeah. Won't be my problem. Yeah, well, first question, say places like Truckee get their water from Donner Lake. So again, that's a water body within the greater Truckee watershed. So Tahoe is at the head of the Truckee River watershed, and then Donner Lake and several other reservoirs are down further. So the water, most of the water that isn't drawn from Donner Lake goes to Reno. So there's urban use there, there's the Newlands irrigation project, and then the residue goes to Pyramid Lake, which is a whole story. Second question, what else is killed under the mats? Everything. So it's a very indiscriminate technique, unfortunately. But what we were able to do is since we did these initial tests, we've been able to keep monitoring for 3 years, and the rate of return of Asian clams is low. The rate of return of the native species is much higher. So again, I tried to say this is a control. It's aimed at controlling them. Eventually, the same thing may have to be done again. What we're trying to figure out is, well, whether you have to do it every 5 years or every 15 years. And we don't know enough yet. I should say we did small scale tests, 5 acres now, 1 acre before. There's probably on the order of 200 acres to treat. The third question was, well, actually it was a mixture. There was early stuff, then January was really dry, and then you're right, it was snowing right through June. So, but I think the urban runoff is still the same. There were still people there. There wasn't a major drop-off in urban runoff, so it seemed from the little bit of data we have. That's one thing that agencies aren't funding is urban stormwater. So there is no. I'd love to have a long-term data set for urban stormwater. It doesn't exist. Well, it's doable, and that's under the TMDL. That's the sort of thing that local jurisdictions would be getting credits for. Groups like Caltrans have some detention basins. The problem is that these are very fine particles. So detention basins are great for collecting sand, but this stuff flows right through it. So that's one question, is how to better design them or come up with better techniques, maybe spreading it over, pumping it up and spreading it over a meadow or something like that. But that's actively being done. Unfortunately, the way these credits are being assigned is on the basis of model results. Well, the model says that a detention basin gives you 2 credits. Nobody's actually going out and monitoring any detention basins to see whether they're doing what they're supposed to be. Question here. Yeah, it would be a source. We don't get any from it. We get a little bit from the Nevada license plate, but again, it's not regular funding. In Nevada, they have a call for proposals every year, and you write proposals along with everybody else. Yeah, Tahoe license plate would be a possibility. Right, Tahoe license plates. Yes. Okay, so that dam, the outlet to the dam, this is the beginning of the Truckee River. There's a dam. It was put up in the 19th century. It's 6 feet. That's all it is. If it was removed, you would have posses coming up from Nevada trying to find the person who removed it, because that's the water that is allowed to be taken from Tahoe for downstream use. So you can't remove it without violating a whole bunch of water law. What the physical effect of removing that would be is that all the property owners who have docks around the lake, many of them would find their docks ending short of the water. And every 5-10 years, it goes down to the natural rim of the lake, the bottom of that dam. But then somehow, I think the longest it's ever stayed below that may be 3 months or 6 months, something of that order. Our big fear, we did a study on this as well, if you had a 10-year drought, what would happen to water levels? And it's pretty amazing that in some parts of the lake would be half a mile from the current shoreline. So clearly, removing the dam would sort of bring that day a lot closer, because you'd be fluctuating from a much lower level. Whether it has a shoreline erosion because of the higher water levels is a small contributor. So I don't think physically, for the clarity of the lake, the dam is a major. Yes? Sorry, say that again? Yeah, the stable stratification is, I mean, that's the trend line. But if you looked around that trend line, it was all over the place. I personally think that the deep mixing, I think the last 5 years we've had 3 years of deep mixing. I think that's just unusual. Just a lot of noise in the system. No, I meant deep mixing is noise in the system. It's a different noise in the system. But it's an example of the same thing. Yeah, and I think it's not just a Tahoe issue. So this is the same issue that's going to affect every dam, I believe, in the state. Many of them do lose their oxygen in the summer, and agencies deal with it. You get manganese released into the water and iron, and they treat it. It's a water treatment cost. But if it isn't just happening for 2 months, but happening 6 months a year, 9 months a year, then those costs are going up. And so it's just part of this question of this whole issue of climate change not just affecting water quantity, but also water quality. Yeah. Well, for that particular scenario, so I think rather than the exact year, it's sort of let's think of the second half of this century rather than the, yeah. Unless, yeah. The A2 used to be considered, I think, that was considered reasonably high, but I think if you look at the last 10 years, we've been releasing carbon at more than the A2 emission rate. So it used to be considered high. Now we're hopeful of that. Yeah, there are a lot of things that are being tried. There was a lot of hope for permeable pavement. With the sort of ice and snow, I don't think they've resolved, or they've even found what all the issues are. If it's permeable, does it start breaking down because of ice formation? If it gets, how do you clean it? It works great, but after 5 years, then what? I think they're the issues people are thinking about now. And street sweeping is one thing, as mundane as it sounds, has been found to be incredibly effective. Not just the street sweepers that have brushes that go around and put everything in the air, but the ones that actually have vacuum and remove the fine particles. It's probably as effective as any detention basin. Yes. Oh, yeah. Yeah, and we always have to sort of make the distinction that we do the science, and we don't do these projects. We say the problem is with the fine particles, and we tell them that, and we have workshops and the like. But if they go and do something else, then that's how it works. But we actually have good relations with them. Their mission is very different than ours. Pleasure.